Welcome back. Today we're going to be looking at section 3.5, which is the transformations or shifts of functions. We're going to be shifting functions to the left, to the right, up, down, seeing what happens with compressions, stretches, and those kinds of things. So we're going to be taking the functions that we've already had and been graphing, and those toolkit functions from the chapter 2, and transforming them in some way. So let's go ahead and get started. We will start with addition and subtraction. So the first thing, and the most common, and you've probably seen it before, is this idea of a vertical shift, which is when you shift a function vertically, either up or down. And you look right here, you see that orange picture. If you add 1 to the outside of your function, or after your function, or as a constant to your function, it goes up 1. So you could imagine if you were to subtract 1, maybe in a different color, f of x minus 1, you'd probably get a full shift down by 1. And it might look something, maybe a little better if the computer built it, but like that. So we've got up and down. And so this long word problem I thought was worth keeping in here because the word problem basically phrases it all as, hey, I've got you a function, a pretty common function with half of gravity, half of Earth's gravity going down, and I want to throw a ball and see what happens if I change throwing the ball from the ground or no height to any given height, right? So all we're going to do, not any given height, to exactly 10 meters. I want to throw it from a 10-meter building. So what you had in the first place was a guy throwing a ball from the ground and it looking like a parabola. As time went on, the height looked like a parabola, and now you've got a guy on top of a building throwing the same ball and saying, hey, that's also a parabola with a negative time area in that red zone. How did it change? And basically the only thing that happens is, like we just said, to vertically shift something, if it's not moving left or right, all you have to do is add something to the outside or add it outside of the function. And so b of t, the new function, is going to be exactly the same thing, leaving all of the variables alone and adding 10 to the outside. And that's it. Vertical shifts are probably the easiest to graph on a graph and to write in an equation, so that's why we start with it. Horizontal shifts are a little bit differently because they have one thing different, and that's that they flip-flop. What you expect to happen might not be what happens because you're affecting the variable in the input instead of affecting the output. So we added 10 to the output, which means we added 10 to our graph. But if you add 10 to your input or subtract 10 from your input, you're going to go the opposite way that you might expect. And so here you can see they've added 1 in orange right there above. They've added 1 on the inside of the function, or they've added 1 to the variable of the function. And what that does is shift the graph by 1 to the left. Likewise, if you subtract 1 from the function, it'll shift the graph to the right. So it might be opposite of what you'd expect. And so here, we've got a pretty straightforward question where they said, we've added 2 to the input of the function. So what happens? Is this a horizontal or vertical shift? Well, because it's on the inside of the function, or it's affecting the variable, it's going to be horizontal. And because it's plus 2 and it's inside the function, it's going to go flip-flop of what we'd expect. So instead of going to the right 2, which you might think because it's positive, it's going to end up going to the left by 2. So it's a horizontal shift to the left by 2 units. And if you want to add the word units, just to be safe, it's a horizontal shift to the left by 2 units because it's plus 2 on the inside of the function. So here we go. We're going to apply both of these things in the same function and see what happens. First thing they ask us to do is to graph our parent function of f of x equals the absolute value. If you've been studying those toolkit functions from chapter 2, then you should be pretty familiar with the absolute value function. It looks a little bit like this. I'm going to make my toolkit function red. I think that's good. Make sure I didn't do anything crazy. So I'm going to label the red function as f of x equals absolute value of x, and then I'm going to ask what transforms did they do to the function. Well, in green, it looks like they took it up by 4 because it's positive 4 on the outside of the function. And in orange, it looks like they shifted it to the right by 2 because it's going to the right because we've affected the input. If it's on the inside, flip of what you would expect. If it's on the outside, it's exactly what you'd expect. And so I'm going to take each point on here, this red point right here, and I'm going to go to the right by 2 and up by 4 to plot a new point. Let's make it, light blue. To the right by 2, up by 4. And then what we're going to do is just take the exact same function, which we know goes up 1 over 1, up 1 over 1, up 1 over 1 forever, and up 1 over 1, up 1 over 1, up 1 over 1 forever, because it's kind of how the absolute value works. So that is not f of x anymore. What did the problem change it to? H of x in blue. So there we are. We shifted it to the left by 2 and up by 4. Every single point on the graph. If you want to do that for every point on the graph, you're more than welcome to. I only did it to 1. All right, let's hop down and look at reflections now. It's very, very similar to the other one, whereas you can see the vertical reflection is being affected on the outside of the graph, and the horizontal reflection is being affected on the inside of the graph. And the reflection comes just from a simple negative sign. That's the only thing that does it. You throw a negative sign on the inside or an affecting variable, you get a horizontal reflection. You throw it on the outside, you get a vertical reflection. So let's hop down and see what that happens. They gave us another absolute value. That's fine. We will graph f of x first. F of x is the normal absolute value graph, but taken to the right by 1. And so let's make f of x red and just take the normalest absolute value graph, but go to the right by 1. That's not good. Is that better? Yeah. The normal absolute value graph, up 1 over 1, up 1 over 1, but go to the right by 1. There's f of x. Now it's saying, hey, reflect it vertically. Okay, so vertically, what does a vertical reflection means? Well, it means that every point on the graph, if we want to call this new graph h of x, is going to be negative where it was positive. So it's going to have a negative sign on the outside, and it is just going to look, if we're doing green, I'll do line. Up 1 over 1. Now, up 1 over 1 turns into down 1 over 1, down 1 over 1, down 1 over 1, until we get to the end, down 1 over 1, down 1 over 1, until we get a pretty line, like that. And we reflected it vertically. All right. Let's look at this table real quick and do one quick reflection, because the reflections on a table might be a little more confusing. Graph, pretty straightforward. You're going to flip it. Whichever way it asks you to flip it, you're going to flip it. Table might be a little more confusing, so the easiest way that I think to do it is just to apply the reflection using the symbol. What I mean by that is I've got g of x already, and I've got f of x in a table, and all I'm going to do is add the symbol where I see f of x. So maybe this works best by adding a whole nother section. And instead of writing g of x and leaving it abstract and new, I'm going to write negative f of x. I'm going to say, oh, well, negative f of x is just whatever the f of x was, but negative. And then, at the end of that, I can throw a g of x next to it so I don't forget what column that was, or what row that was. So we got our g of x is negative f of x. Now what about on the inside? What about if we need to make a table of values for a negative on the inside for h of x? We've got f of negative x. That one's a little trickier. 1, 2, 3, 4. Because what used to be negative is now positive on our input, not our output. And so what would be, let's say, f of negative, what is f of negative 2? Wasn't that just the same thing as f of positive 2? So the input's flipped here. So I know that got a little abstract, but let's throw in some real numbers and make it happen. So if you were to plug in x equals negative 2, f of negative 2 is just f of 2, right? So now let's go look at our normal f function for 2. Say, well, f of negative 2 would be 15. And you'll see what happens is these numbers kind of flip over the 0. Let's check out on 0. So what is f of negative 0? Oh, well, that's just going to be f of 0. So 0 is just going to leave us with 15. Oh, not 15. 0 is going to leave us with 10. Now we've got f of negative 2. Oh, which is already on our table. We can just look at f of x and go over 1. And that's going to be 5. And what you'll see is you see over that line that these two numbers flipped, which means you can guess that this 4 of 20 is going to come over here. But we've got a little problem in as much as we don't really know anything else about this function besides the number that they gave us. So we don't know what f of negative 4 is, which means it's really impossible for us to know what f of 4 would have been. And we are going to leave that spot blank. But that means that we probably do know, if we wanted to go to the other side of our graph, what f of negative 4 would have been. We don't need to do that, but you could. You go ahead and say f of negative 4, we know for a fact is negative or positive 20. So if you wanted to take this whole table, move it over a little bit, and add a new column that wasn't even on our first table, you are legally and mathematically allowed to do that. This is our h of x column, and we know negative 4 because we're adding a negative sign to the input is going to equal 20, where that blue line just got reflected. Awesome. All right, while we're talking about all this stuff, these negative signs, positive signs, these moves of the graph, it's also pretty important to talk about even and odd functions. We're going to hit this later as well when we get to invertibility, and when we get to inverse functions a couple of different times in the year, but it's really good to call it out now because it's just going to keep coming up over and over again. So if you can put this negative sign on the inside, like we did, so what, maybe a good question to ask is, what does that represent? What does that negative on the inside represent? That represents a horizontal reflection, right? So if you can reflect it horizontally, and the graph stays exactly the same, nothing changes about it, then it's symmetric about the y-axis, and it's even. Well, that makes sense. If you can reflect it across the y-axis, it better be symmetric across the y-axis. That's like, there's tons of functions that we know that do that. You could think about well, maybe not the absolute value function, but you could think about x squared. You could think about x to the 4th. You could think about a negative x squared. Tons of functions that are going to do this. An odd function say, well, hey, if you can reflect it vertically, or if you can throw a negative on the outside, then it's not necessarily symmetric about the y-axis, but it's symmetric about the origin. If the vertical reflection ends up being exactly the same, we're not saying it's symmetric across the x-axis or vertically. We're saying that it's symmetric about the origin, or it's odd. Good way to remember that. Odd starts with O. Origin starts with O. Pretty easy way to remember that. Even starts with E. Nothing else starts with E there, but I like to remember odd, origin, even, y-axis, or vertical. All right, so here we go. Let's check it out and see. What we're going to do is we're going to plug a number in. We're going to plug a negative in and just see what happens. So what about f of negative s? What happens if we check? If we were to flip that negative s, we'd probably get negative s to the 4th plus 3 times negative s to the squared plus 7. Well, we know that any number raised to an even power, that negative sign is going to end up canceling itself out over time because you're just going to end up with negative 1 times negative 1 times negative 1 times negative 1 4 times, and then with 4 s's on the outside if you were to factor out a negative 1 a bunch of times. And so any even power is going to eliminate the negative sign and leave you with s to the 4th, s squared, and 7. And that f of negative s is exactly the same as f of s. And so what we know is that this is symmetric. First thing first, we know that this is even. Second thing we know is it's symmetric about the y-axis, or it appears to be reflected horizontally. Cool. And if you want to check that out in your brain, you're like, I don't know if I believe you with that math stuff, just think about what function this is. This looks a whole lot like a quadratic, but way wider because it's a quartic to the 4th function, right? And it's going to be raised up 7. It's going to be positive facing up. So it might look something like that. And we'll see symmetry about the x-axis for sure. Alrighty. Last but not least, we're going to write one function because I think it's a really good one to try to go from a graph to an equation instead of from an equation to a graph. And so we're going to say, what does this function kind of look like? The toolkit function, or the parent function, might have looked something like x squared, right? Probably. Where you start on 0, you go up 1 over 1, up 1 over 1, 2, 4, 2, 4, and you draw your line. Well, first thing I'm going to do is check the pattern. Say, is this about the same pattern? We've got up 1 over 1, up 2 over 4. Yeah, it looks about the same. So now we just have to decide what the shifts were. Well, it looks like it went to the right by 1 if I just look at the vertex. I'll show you what I'm looking at when I'm doing this. I'm just looking at that vertex right there, and that vertex right there. And it looks like the vertex went over to the right 1. So it means the whole thing went to the right 1, which means it's f of x plus, nope, because opposite of what you might expect, minus 1. And then it also looks like it went down a certain amount. Let's count. 1, 2, 3. Looks like it went down 3, which means we've got f of x minus 3. We'll put those together with that toolkit function that we expect it to be from memorizing all that in chapter 2. We're going to end up with f of x minus 1 minus 3. And when we apply that to that toolkit function, we end up with x minus 1 on the inside squared minus 3 is probably our f of x. If you want to go on Desmos or Google or a calculator and try to check that and make sure that looks about like that other function that we just had, that's a good idea. All right, thank you for watching. As we get closer to the end of chapter 3, it's important for you to go back and watch through some of the videos we've been doing, try some practice problems, try some exercises that are in the section, and do as much as you can to prepare yourself for the test that's coming up for chapter 3 and all of these functions and function notations and things about functions that we've been working on. Thank you for watching, and I'll see you next time.